Yeah, it's a little intro, musical intro there from Blood, Sweat, and Tears. This little video is going to be talking about circular motion, and in particular, things that travel around in circles and their particular own type of velocity. So I want to talk about two different kinds of velocity, linear velocity, and the other one is called angular velocity. All right? Now, linear velocity is the one that you're probably a little bit more familiar with concept-wise, because really all it means is a change in distance over time. Just like your very familiar little formula from science class is v equals d over t. Velocity is distance divided by time. It's that exact same concept. A point traveling around the circle over time. That's its linear velocity. Now, angular velocity is a little bit different. That's not the change in distance. That's a change in central angle over time. Okay? A little bit different concept there about angular velocity. Sometimes we use this phrase RPM to describe angular velocity, how fast the central angle is changing over time. Some things travel very fast in circles, like the wheels on a car or machinery parts, or maybe the CD in your CD player, something like that. Those things are spinning around very fast. And so using a concept of like revolutions per minute, or maybe revolutions maybe per second, or some other unit of time, you know, would be used to describe the angular velocity. Okay, well, let's take a look at the mathematics on these two types of velocity. Linear velocity first. Distance over time, and on a circle, really, when we say distance, what we're really talking about is arc length. Okay, so you could say then that the linear velocity, instead of d over t, that's distance divided by time, you might think of that as arc length divided by time. However, I am going to add a little asterisk there about that, because that formula, arc length over time, while 100% true, is going to be more useful to us in a slightly altered form later. So just kind of hang on to that for a second. All right, so let's talk about angular velocity then. Angular velocity as a change in central angle over time. Well, in our study of trigonometry, we use the variable theta to represent the central angle in a circle. Okay, so we're talking here theta over time. And that little letter right there, that thing that looks like a W, that of course is our friend omega. So omega equals theta over t. That's our little formula for angular velocity. Let's focus on angular velocity here for just a second. Give you a couple of examples to ponder. I had a Ferris wheel picture up there earlier. So let's say we have a Ferris wheel that makes one complete revolution in 45 seconds. Let's find the angular velocity of that Ferris wheel. Well, it's pretty simple, really. The phrase one complete revolution, all right, that is 2 pi. That's 2 pi radians, right? One revolution, once around the circle, is 2 pi radians. So if angular velocity is just the revolutions divided by time, it's just 2 pi divided by 45. And take a look closely here at our units, radians per second. 2 pi over 45 radians per second. Okay? You can think about that if you want for a second there. That is going to be very important to us later on, and you'll see why. Here's another example, though, about angular velocity. Let's say something going pretty fast, a bench grinder. You find that in machine shops or wood shops sometimes. Bench grinder going 1,800 revolutions per minute, RPMs. Well, once again, one revolution is 2 pi, and if it's going 1,800 of those in 1 minute, then it's 1,800 times 2 pi for 1 minute. That's the angular velocity there. So we could say, just to simplify that, 3,600 pi radians per minute. Okay, so there we have radians per minute on this. All right, so let's go a little bit farther in this, and I want to bring back that little asterisk that I had up there earlier. We know that arc length equals radius times the central angle in radians there. That formula, S equals r theta, is pretty well known to us, I hope, and it's pretty simple anyway, if it even isn't well known just yet, but it will be. And so now we have this S over t for linear velocity. Okay, well, let's try this. Replace the S with r theta. Okay? So r theta, radius times theta over t, that's our linear velocity. But wait, there's more. If I do a little algebraic manipulation of that fraction and have it r times theta over t, well, your short-term memory hopefully kicks in right here, and that theta over t should look familiar because that's what we just said angular velocity is, theta over t. So what that means is that our linear velocity, v, is simply r times w. Linear velocity equals radius times angular velocity. So there's this proportionality idea between the linear velocity of something and the radius. And if you went back and looked at that wind generator blade that I had earlier, think about that spinning around. If you've ever seen those, they are gigantic things. And a point on the very tip of that blade is traveling around in a gigantic big circle. And it's going really fast, even though the blade seems to be kind of cruising through the air. A point right near the hub of the blade is traveling, so-so. It's going around in a circle. I don't know how fast they travel, but not that fast when you compare it to a point on the very end of that blade. That is really zooming around in a circle because the radius is so big. So the angular velocity is constant for the entire blade, but the radius determines what the linear velocity is at any point on that blade. Okay? Hopefully that's a little just talking through that example here. Let's take a look at our bench grinder problem again. Let's say we've got a 6-inch bench grinder rotating again at 1800 RPMs, and the question now is to find the linear velocity of the edge of the grinder wheel in inches per second. Okay, 6-inch wheel, 1800 RPMs. So we've got the velocity is radius times angular velocity. We had previously just figured out that the angular velocity of that wheel is 3600 pi radians per minute, and we are now just told that the radius of that wheel, I should say that's a 6-inch radius bench grinder wheel, sorry about that. You might think diameter there, but the radius is 6 inches. That's a pretty big one. So that is 6 inches there, and so now what we do is we just put in the numbers in our linear velocity formula. So 6 inches times 3600 pi radians per minute. Well, great, that seems pretty easy. However, we are asked to find it in inches per second, not inches per minute. So we do our simple little thing from physics class called dimensional analysis, you might call it. We're going to multiply that fraction by another fraction that equals 1. Right? 1 minute divided by 60 seconds, well, that just equals 1. So we're not changing the value, we're just changing the units. And that allows us, of course, to cancel out the minutes and the minutes. And one more idea here, the radians are not a unit of measurement. They are just a real number. So they kind of disappear in this whole process. There's no radians anymore once you multiply it through. When you just multiply it through, you just get 360 pi inches per second. By the way, 360, that's what you get. If you take 6 times 3600 and divide it by 60, you get 360. So 360 pi, going along for the ride there, inches per second, which probably is more usefully expressed as 1131 inches per second just by multiplying there. So that's our video. It's a little bit longer than some of the ones I've made. Hopefully it's a good illustration of some of these ideas. Don't forget about the unit conversion. That's going to come up. Don't forget about the fact that radians kind of disappear from that unit conversion process. And hopefully you can get your mind around this idea that the linear velocity is simply the radius times the angular velocity. Okay, thanks for tuning in. Bye.